In today's notes, we're going to revisit transformations that we saw in the first semester as we dealt with linear transformations. Linear transformations are kind of boring because lines are boring. So if we have a line and I move it up or down, that's pretty much the same idea as moving it left or right. I could accomplish the same thing because there's not really any interesting features. But for other functions like quadratics and other polynomials and all other kind of functions, translations and reflections and all of that become more interesting. So we're going to apply all of the same kind of rules that we used in linear transformations, and these function rules in our notes, you may notice, look exactly the same. The one thing here is that in Algebra 1, we're going to ignore the idea of B. So if you remember, B controlled a horizontal stretch or compression, and it controlled a horizontal reflection. So one of the reasons for that is that reflecting a parabola or a quadratic function horizontally is really boring because, as we've already learned, there's a vertical axis of symmetry. So if we reflect over that, then really nothing changes. So horizontal reflection, not too interesting. Horizontal stretch is just complicated. So dealing with the idea of how it's a reciprocal, like we talked about in linear transformations, we're just going to ignore B altogether for this section. So that only leaves us with A, H, and K, which are the same kind of transformations that we dealt with lines. Like linear functions, we start with a parent function, f of x equals x squared, and then we apply rules to it in order to transform it. For example, our first function rule here, f of x plus k. So if I said f of x equals x squared, and my new function g of x equals f of x plus 7, then my transformed function would be g of x equals x squared plus 7. I just add 7 onto whatever all of f of x is. So this x squared came from here, and then at the end I added 7. Whereas if I had a horizontal translation where I had f of x plus h, and I started with my parent function, f of x equals x squared, and then we said g of x equals f of, and then in parentheses we put x plus 7, then that would work out a little differently. We would have f of x equals, and then anywhere that we see x, we replace x with x plus 7. So my new function would be x plus 7 squared instead of x squared plus 7. And we know that that's going to cause a horizontal translation. So let's do a quick recap. But I wanted to go through this just to remind you there's 3 stages here. So there's the original function that we're transforming, which in this case was the parent function. Doesn't have to be. There is the rule or function rule that's transforming the function. And then there is the final transformed function that we end up with. So that same 3-step process that we learned before applies here as well. So same deal as with linear. Vertical rules happen outside the parentheses, and horizontal happen inside the parentheses. So remember we said that that goes with the idea of vertical affects the output, so it's outside, and horizontal affects the input, or x, so that's inside. So the rules, same exact ones as we had before. F of x plus k shifts up by k units. F of x minus k shifts down by k units. Negative f of x is a reflection, so that is a reflect over the x-axis. So vertical reflection, which is going to turn, and we've already seen this, right, is that this is a normal parabola, but we can flip it upside down so that it has a maximum if we put a negative in front of our a value. A times f of x, so this is what causes a vertical stretch. So this is vertical stretch by a factor of a. And then if a is greater than 1, so that's going to turn this parent function into something steeper. And we add a new idea or vocabulary for graphs that have shape like this. We say that this is narrower. So vertical stretch goes along with a narrower graph. Vertical compression squishes the graph down and makes it flatter, and we call that wider. So when a is 0 to 1, then we vertically compress by a factor of a. So those are all of our vertical changes. They're exactly the same. The only two new ideas are these two terms. So with lines, when we vertically stretched, we called this steeper, and we called we called a vertically compressed line flatter. So instead of steep and flat, which is specific to straight lines, we, with more complex functions, use narrower and wider to talk about the shape and how it got either taller or fatter. Horizontal rules are really simple because all we're doing horizontally is translating. We are not reflecting and we're not stretching and compressing in Algebra 1. In Algebra 2, they'll bring that back and it'll be, more complex. But for now, we're just shifting. But it is backward like before. So we might want to put like a exclamation or a star here that says backwards so that we remember that the general form, when we have x plus h, we're going to the left, even though plus is right. All of the horizontal stuff is backwards. F of x minus h shifts us to the right. So exactly the same as what happened with lines and any function. So as a reminder, these things we're talking about here, these function rules, can apply to any function in existence. It does not matter what kind of function it is. So the rule, this middle part, applies to anything. It can turn any original into any final, but the rule would be the same no matter what thing we're transforming. So as a side-by-side, just before we move to the next page, if we had f of x equals x, our linear parent function, we can apply this exact same rule. G of x equals f of x plus 7. The rule is identical. But then when we apply it, we'll get g of x equals, and then wherever x is, we replace it by x plus 7. So we get another line that's shifted up 7 units. This one, and that's the thing, is that ended up equating basically to a vertical translation. That does not happen for a parabola. Because you can imagine if I move it left or right, I can't say that thing in terms of moving it up and down. Whereas a line, if I move it to the right, well, it's basically also like I moved it straight down. It makes no difference. For shaped graphs that aren't straight lines, it does. It makes a big difference whether we're moving horizontally or vertically. So let's look at a few example problems for all of these. And we're going to go through one of every kind of thing here, and we're always in these transforming our parent function, f of x equals x squared. So shifting up and down, the number is added or subtracted outside the parentheses. If we want to shift up by 2, then k is equal to 2. Our function rule says g of x equals f of x plus 2 outside the parentheses. And our applied function would be g of x equals, and then we would have our original function, x squared, and then plus 2 added on to the end there. Shifting down is the same exact idea, but we have a negative k value. So our g of x would be equal to f of x minus 5. Our applied version would be g of x equals x squared minus 5. So just our normal x squared function, but shifted all down by 5. And if we drew those on our graph, the curvature stays the same, but my y-intercept, it looks like we're counting by 2's here, so my y-intercept on the first one would go up to 2, and then it would have the same curvature as the original. And then the second one would go down to negative 5, which would be right here, and again, same curvature as the original, which I always struggle to draw on the computer, but you get the idea. It shouldn't be any wider or narrower. It should just be moved straight down. Reflect over the x-axis. Our function notation is g of x equals negative f of x. So it reverses all the y values, And the applied version here would be g of x equals, and then we put a negative before we write what f of x was, so negative x squared. Remember that in our order of operations, the x is getting squared, and then the numbers are becoming negative. So if we took our parent function and reflected it like this, it would flip upside down and look like that. Vertically stretched by 3. So a is going to be equal to 3. Our function notation, g of x equals 3 times f of x. And we would get our applied function, g of x equals 3x squared. It's a really bad square. Okay, 3x squared. So in this case, we're squaring the x values and then tripling them. And what happens is we get 3 times steeper. So the graph grows, same y-intercept, but it grows much more quickly. It's a much narrower, so vertically stretches narrower graph. Vertically compressed by 4. A is going to be equal to 1 over 4. And we're going to have a wider graph. Wider graph. So here, g of x equals 1/4 f of x. Our applied function notation is going to be g of x equals 1/4 x squared. So this a value literally becomes the a value in the quadratic equation where we had ax squared plus bx plus c. This a value literally is the vertical stretch. So the coefficient of x squared is telling you the vertical stretch or compression. A vertical compression is going to be a wider graph. So it's going to be something like this. I could actually calculate values, but I can't draw well enough on here to make it worthwhile. So we'll just draw it roughly like that for right now. If we did want to find the points, though, you may have seen on page 1 there was a table. This table had all of the kind of basic values for the parent function. So let's talk about if we wanted to properly graph that last one. What we would do is we would take our x and y values, and we would start with our vertex in the middle, which the vertex here didn't move. It's still 0, 0. And then we would go a couple of spaces in each direction. So -1, -2, 1, 2. So as we go to the right one step, we normally would go up x squared, but instead we're going to go up 1/4 of x squared. So instead of ending up at 1, 1, like a regular parent function, we're going to end up at 1, 1/4. Then as we go 2 steps forward, we normally would go +4, but we're going to go +4, 1/4 of 4. So we're going to go to 1. So actually I was pretty close. I got 2, 1 right here. I didn't quite hit it over here, but pretty good. So that's how we can use a table, is to start with our vertex wherever it moved based on h and k, and then go a couple of units in each direction to find more points by plugging in x values. Okay, horizontal rules. Shifting left and right, remember that it is backwards, always opposite of what you think they should be or what intuition says they are. Maybe by now you know it correctly and you think about it right, but our intuition says that positive is right, negative is left, but this is exactly opposite of that. So again, starting with our parent function, we want to go left 4 units. So our h value is -4. Our function notation, g of x equals f of, and remember these changes are happening inside the parentheses, and since our h is -4, we're going left 4 units. When we write our function rule, we see x plus 4. So this is the step where it becomes backwards. The h value is still -4. If you think about our axis of symmetry, once we move left 4 units, we're going to be right here. And our axis of symmetry, which is h, is at x equals -4. But our function rule is x plus 4. Our applied function notation, we're going to just leave as where x was, we put x plus 4, and then remember we have a square applied to that. So the rule and the applied version look very similar here, but they are different because the rule doesn't have a square in it and the applied function does. Shifting right to h is going to be 2. We're going to do the backwards thing of that, so f of x minus 2. And then we'll have g of x equals f of x minus 2 squared. Oh, I don't know why I put f there. My bad. Let's erase that. No f in the applied one. F is in the rule. Okay, so let's look at what would happen there. So with the plus 4, we moved 4 to the left. With the minus 2, our vertex moves 2 to the right. We didn't multiply by anything, so we still have the same curvature. So it's still the same kind of parent function width, like that. It's not any wider or narrower than the parent function. I kind of drew the first one a little wide, but again, I can't draw very well on the computer, so you just have to, use your imagination and pretend that I'm better at drawing and that this is the right width. Okay. So that's all we have for horizontal. Remember, we're not doing reflections and we're not doing stretches and compressions. There's no B value, only A, H, and K. And we're going to do a couple of composite transformations, ones where we do multiple things in order to see if we can apply these rules to it. So it says, how would this graph be affected by the following things in this order? So we have 3 rules to apply. We're going to start with f of x equals 2x squared plus 2. We're going to apply the rule to reflect over the x-axis is negative f of x. So that means we're going to do negative 2x squared plus 2. So after our first transformation, we're at negative 2x squared minus 2 because we have to distribute this negative to both terms. The next rule we want to apply is vertically stretch by 2. So that means the rule is 2 times f of x, but now we're applying it to this kind of intermediate step. So we have 2 times everything. That's negative 2x squared minus 2. We distribute the 2 and we get negative 4x squared minus 4. This is our second intermediate step. Our final transformation is to shift left by 3 units. To do that, we're going to put the rule f of x plus 3, and then we'll replace this x with this x plus 3. So our final transformation is f of x equals negative 4. That doesn't change. Then when we see our x, we're going to plug in or substitute x plus 3 squared, then minus 4. So we didn't change anything about that last one except the x, because the horizontal transformation only changes x. It doesn't change a or k. So that's our final version is, we'll call it g of x since we changed it so much. G of x equals negative 4 parentheses x plus 3 squared minus 4. And this is kind of an overview of what we're going to do next with this topic, which is to talk about a different form of quadratics. So we've gotten used to factored form and to standard form. This one that just basically shows you the transformations and we don't multiply out that x plus 3 squared is called vertex form, and that's our topic for this week. It is the best form for most functions, quadratics and others. So this form just shows you exactly what the transformations are, meaning it's the easiest to read from a graph and the easiest to draw on a graph. It tells you your vertex immediately because we see h here and k, or negative h and k. So we know our key features really quickly as well. This is a really, really powerful form, and it's generally like the best form for quadratics in most ways. We can always turn this into standard by multiplying out the x plus 3 times x plus 3, distributing and all that, and we'll talk about that later in the week. All right, last one on this notes, we have how would this graph be affected? First of all, they don't tell us the equation of the graph. That means we're going to use this idea we just talked about to read the graph. So we see The changes that have happened is we went up 2 units, we went left and right 0, so 2 is k. H is 0 because we didn't move left or right. We're still sitting on the y-axis with our vertex. And then looking at how fast the graph is growing, we have right here, we've gone up 2 and right 1. We know that on our parent function, when we go right 1, we go up 1. So we went up twice as far. So that tells us A is equal to 2 in this case. Okay, so we can use that to write the original function. I'll do that over here to the right. I'm going to get a different color just to differentiate problems. So we can write this one, the original f of x is equal to a times, then we look at our h value, so we don't have any, so it's x minus 0 squared, and then plus k, which is 2. So original function was 2x squared plus 2. Hey, that's the exact same one as this, but from a graph instead of written out. Neat. So first we want to vertically compress it by a half. We know that that rule is 1/2 f of x. So we do 1/2 and then distribute it to the entire thing, 2x squared plus 2. When we distribute, we come up with x squared plus 1. So that's our first intermediate step. The next rule we want to apply is shift down by 4. So we can do f of x minus 4 for that rule. And we would get, when we apply it, our new version would be x squared plus 1 minus 4 is a total of minus 3. Then finally, we want to do shift right by 2. That's f of x minus 2. And our final version in vertex form will be, we don't have an a value, so we just go straight to this x and plug in x minus 2 in parentheses. X minus 2 squared minus 3. And that's it. So our final version here, g of x equals parentheses x minus 2 squared minus 3. So this graph is a bit wider than that one because it started with an a value of 2 and ended with an a value of 1. And it is shifted down and to the right. So it's going to be down 4 units. So it's going to be, well, it's compressed first, then it goes down 4. So we end up at -3, 1, 2, 3, and right 2. So this is our new vertex. Remember, we get that from this is h and k, or sorry, negative h and k. And then the this is now just 1 for the a value, so we know that we want to go to 1, and then at the next one we should be up by 4 from the vertex. 1, 2, 3, 4. And we can kind of use a couple of points like that to guide us. Something like that. Okay, so that's all for the notes. There is some practice on identifying these things from tables, graphs, and others, so I'm going to look at a couple of these to round out the video. If you don't need help with this, then by all means go work on it. But I thought that we would just look at 1 or 2 examples from here to make sure we're clear on what we're doing. So on number 1, it asks what transformations were made to create the new one. So we're going from f of x to g of x. And in a table, the most important thing is for us to find where the vertex is. So if you look at the y values, they are decreasing from here to here, but then they start increasing again. So basically this line in the middle, not because it's in the middle, but because it's where the y values turn around and go the other way, that is our vertex. So the vertex tells us 2 of the 3 things we need to know for transformations. It tells us h and k. In this case, it tells us that we went to the left 3 units and that we went down 2 units. So we have 2 translations, left and down. Then we need to know if the stretch, oh wait, I'm sorry, this is the original. We're supposed to say how it changed from one to the other. I was just saying how this one changed from the parent function. So in the one on the right, the same thing. We are decreasing to the vertex and then increasing to the vertex as our x values increase. So that means that we are not reflecting. We don't have a reflection because the y values are going the same way. So they're increasing, then decreasing. So thinking of a graph, it's going like this. And so was this one. This one, oh wait, no, it's decreasing, then increasing. Whoops, backwards. Okay, so decreasing, then increasing like that. And the one on the left also was decreasing, then increasing. So there's no reflection. Then we need to look at how much the y increases for each step. So from 4 to 5, we went up by 1. From 4 to 8, we went up by 4. So we know that this one has an a value of 1. The original one went up by 1, went up by 4, so it also had an a of 1. So there's no vertical stretch or compression. So there's no change to a at all. It looks like all we have to worry about here is translations. And we can do that by looking at the vertex. So our vertex originally was at -3, -2, and we want to see where it is now by comparison. So now it's at 1, 4. So if we started from -3 and ended up at +1, h is equal to 4. So we went 4, translated 4 units right. And we went from a y value of -2 to +4, which is 6 up. So we had 2 translations and no stretch and no reflection. So that's how we can look for those things in a table. The graph, we have this graph with a vertex here, and they're asking how the vertex will change with this transformation. I feel confident that you can answer that one. If the vertex of f of x is here, where is the vertex of this one? I think that what we just did in number 1 will allow you to answer that. Just remember that this is -h and k, and that we're transforming the original vertex using those values. Yeah, I think that's actually enough for us to look at on here. And then this is what I was talking about with filling in a table with the values. So maybe we'll do one of those. So interesting that it has the table for the original, but not a table for the transformed version. I might draw one. So our original for the parent function is 0, 0. We go up 1 as we go 1 step away from the vertex, because that's 1 squared. 2 steps away, we go up 4, because 2 squared is 4. Then it would be 3, 9, and so on, right? The y is just the x squared. So our original function is something like that. Oh, it's not too bad. And then we're going to look at these transformations. We're going to list them, and what I want to do here is put kind of a table side by side to show how it's different. So the transformations here is a vertical stretch by 2, a shift left by 4, and a shift down by 6. So we're going to apply those things to our parent function and make a table here with those values. So the first thing we need to do in making a table is to put the vertex in the middle. So our vertex was 0, 0. It went left 4 and down 6. So my new vertex is at -4, -6. From there, I can go up and down by 1s, will generally be fine. So -5, -6. And then fill in the corresponding values. So I have a vertical stretch by 2. So here, instead of going up by 1 squared, I'm going to go up by 1 squared times 2. So I'm going to go to -4. Then from here to here, I would normally go up 2 squared, but I need to double that because a is 2. So 2 squared is 4 times 2 is 8. So from -6, I go +8 and go to +2. If I needed another step, I would be going 3 squared times 2. So that would be 9 times 2 is 18. From negative 6 puts us at positive 12. Remember that we can't go from line to line. Everything always goes back to the vertex. And then we know that the values will be mirrored on the other side of the vertex. So I don't have to calculate those. I can just fill in negative 4, 2, 12, and however far I need to go. Generally with parabolas, you go off the graph pretty quickly, so we don't need to go too far. And to finish up, let's graph this one, and then we'll be done. So our vertex went to negative 4, negative 6 right here. And then plotting a couple more points, we have negative 3, negative 4. So we went up by 2 instead of up by 1. That seems right. We have negative 2, 2. So now we're way up here. And then negative 1, 12. And by then we are up here off the graph. So much steeper parabola for this one. And then we have all the mirror image points over here. So we have that one. We have that one, and then we have one up here. That side's a little better. Okay, so that's how we can do those kind of problems on the homework, and hopefully that will help you to finish out the rest of the problems.